Welcome back, and now we're going to go through a lot of examples. We have 5 examples on the docket, and all we need to do is identify the test to use and then write out the hypothesis test that would accompany each one. Okay, so the second part is a little interesting. We'll see how to do that as we go through these. Okay, so first one, and also I should say before we go through this, you may want to have this tree handy. I would recommend you can A, print it out from my slides, or B, draw it in your own notes, but you'll want that at the ready just for this example, and then also kind of going forward later in the course too. Okay, so first context, researchers believe that hair color prevalence is not the same among men and women. Okay, well, so we have to think, okay, how many populations are there, right? That's our first deciding question. So how many populations are there? Well, men and women, right? So that's effectively 2 populations, right? And so it's 2 populations, and then I'm thinking about, okay, what is the quantity of interest? Am I looking at a mean, like the average among men and women? Is hair color, can I classify hair color as an average? No. So I'm looking at a characteristic distribution. So this is a chi-squared test of homogeneity. Okay, so I'm going to say this is a chi-squared test of homogeneity. Homogeneity, or TO. Okay. Now, in the associated course notes for this, the module notes that are linked in Canvas for you, you might want to look through there for a little bit more information. But when we write out the null and alternative hypothesis here for a chi-square test, we only do it in words. Symbols can be done. It's just painful. Okay, so the null hypothesis would state the commonly held belief, and it would just be that hair color prevalence yep, is the same among men, men and women. Okay, now as we go further in the course, when we get to this, you'll see that the textbook just likes to say HO is false. I don't like that. I think it's just a little too, maybe a little too clever, we'll say. So what I like to do is write it all out, and this would state the researchers believe that hair color prevalence is not the same among men and women. Okay, now to recap this, what I had to first do is use my tree, and I needed to determine the number of populations. So that's where I said the number of populations, there's 2 of them. Okay, so that narrowed it down. Oops, I'm getting ahead of myself. Narrowed it down to this middle part, and then I had to say what was the quantity of interest. Well, that was hair color prevalence, which is a characteristic, and so that led me to a chi-squared test of homogeneity. Okay. All right. Next one. The average amount of time that caffeine stays in a human body after absorption is 5 hours. You believe that the time is actually less. Okay. So again, I need to think first, how many populations are there? Okay. How many groups am I looking at? Well, I think it's just one human body, right? So humans generally. Okay, so it's one population, and so I'm at the 1 population mark. And then from here, I need to decide which quantity am I looking at, or am I interested in. And so that, if I think about this, says you believe time. And so, okay, so it's actually average amount of time, right? So it's an average, it's a mean. And so that means I'm here, and so I'm looking at a T or Z test, okay? And so I'm going to say this is a T or Z test, okay? And then this one, when we write it out, it's actually super nice. We can just do like mu for the symbol and then say, I believe that it's actually less than 5 hours, and then this is 5 hours. And I would just need to define mu here as average amount of time that caffeine stays in a human body after absorption. Okay, so again, I just use that same process of how many populations do I have and what is the quantity of interest, and that led me to a T or a Z test this time because I had one population and I was looking at the mean. Okay. The next one, I want you to try on your own. Okay, so in a high school, the principal believes that the average GPA for a particular grade is different for each of the grades 9 through 12. Okay, so think about populations and quantity of interest. Resume the video when you're ready to see the answer. All right, here's my answer. So first of all, we determined that grades 9 through 12, that's 4 populations. And then we have more than 2 populations, right? And so we're narrowed down to either Anova or test of homogeneity for chi-squared, okay? And in there, though, we're looking at, or in this context, we're looking at average GPA, which is to say a mean. And so consequently, that forces our hand to Anova. Okay, now for the format of the hypothesis test here, okay, this one you would probably need to refer to the course notes again. They are posted on Canvas. We'll mention how to access them in class, but the form for ANOVA in the null hypothesis is to say that all the averages are the same. So I'm just using this as symbol. So mu represents the average GPA for a certain grade. Okay, and then the alternative hypothesis would just say that one of the means is different. Okay, one of those mu i's are different. Okay, and then we're done. Okay, so again, 4 populations, looking at a mean, that forces our hand to ANOVA. Okay, 2 more questions here, and I want you to try each of them before looking at the solutions here. All right, so number 4. This one is a little confusing, only that the population, it says there is a population. It doesn't specify what the population is, but we say that we notice that there is one population, and the quantity of interest is a proportion, right? Because it's talking about a proportion of people that don't wash their hands long enough to kill bacteria. And that's scary. But so since we're looking at a population, one population and a proportion in that population, we're doing a test for proportions. And so when we do that, the proportion, we can write it in symbols as p is equal to 0.95, where p is the proportion of the population that fails to wash their hands long enough to kill harmful bacteria after using the restroom. Whew. Yeah, that's why I didn't want to write it all out. So it's just all the green highlighting is what P stands for. And then the researcher, so the new belief is that the proportion is actually less than 0.95. So he thinks that, or he or she thinks that there is less, that more people wash their hands long enough to kill bacteria. All right, number 5. This one is a little confusing, only because a population isn't specified. So what population are we studying? And so this one, if you notice the context here, it's trying to determine if there's a relationship between activity level and amount of sleep. And so given that we're looking at a characteristic dependency, we'd have to go back to our tree and say, okay, well, characteristic dependency only occurs here, and that's in one population, which makes sense because you couldn't necessarily compare you wouldn't want to look at multiple populations as well as a characteristic dependency. So that's why we assume there's just one population, and then we would use the chi-squared test of independence. Okay, and this is another one with chi-squares. We only write it out in words. So the statement here is actually the alternative hypothesis if you reword it a little bit, just saying that there is a relationship versus there is not a relationship in the null. Okay, so a lot of examples here, and we'll get more practice with this in class. With the hypothesis formats, again, refer to the course notes. They have examples in there for you to use. Okay, and here, if it doesn't specify to write in words or symbols, you can do either. Okay, as long as you do it.